Good morning, everyone. Today's topic is the noise sources in an optical receiver. There are different number of noise sources in the optical receiver, and this topic is related to the optical communication. The subject code is the KEC 058. My name is Mr. Himanshu Nagpal, Assistant Professor in EC Department of AKGEC Ghaziabad. So, first of all, discuss about the photodetector. As we have studied about the different types of photodetector that are PIN photodetector and the APD. PIN photodetector is the simplest photodetector in which P-type material, then there is an N-type material, intrinsic material, and there is a semiconductor. In this photodetector generally converts what? Converts optical signal into the electrical signal. So when we are doing the in the PIN photodetector, the optical signal is converted to the electrical current, and primary photocurrent is produced at the output that we generally show here, that is equal to IPH, or we can also somewhere it will be used at a IP. Clear? Now in the APD is the avalanche photodiode. In this, impact ionization and the avalanche breakdown occurs, and the gain of the avalanche photodiode suddenly increases, that is shown by the M. Clear? In this, the current which is produced, output current, is generally we show here, that is equal to APD, and this APD is multiple of what? M multiply में IP. Clear? But when I talk about the mean square value, this IPT is generally referred to as a I square PD is equal to M square function of M multiply में I square P. Clear? So there are two types of current produced, that is the primary photocurrent, which is output of the PIN photodiode, and the output of the APD consists of two types of photocurrents, that is IPH or primary photocurrent, and also multiplied current, that is IPD. Clear? Generally showed that is equal to IPD. So when the signal from the optical fiber cable is in the form of optical signal, optical light energy, or is strike onto the photodiode, this photodiode converts the light energy into the electrical signal. Clear? So there are number of, and this photodiode is a part of what? Receiver. First part of the optical receiver, first component of the optical receiver, that is first is the photodiode. And generally we can also use the preamplifier which is placed beyond the photodiode, but generally we discussed that the first component of the optical receiver is the photodiode. So there are number of, and after that photodiode the amplifier is placed. Clear? So there are number of sources which is occur in the optical receiver, that is the noise sources from the photodiode and the noise source from the amplifier. Clear? So in fiber optical communication system, the photodiode is generally required to detect very weak optical signal. Detection of weakest possible optical signal requires that the photodetector and its following amplification circuitry is to be optimized so that the signal to noise ratio should be maximized. Means optical photodiode with amplifier should produce the optimized output so that SNR is maintained. Clear? The power signal to noise ratio is designated by the SNR at the output of the, means the SNR is the main parameter which determines the function, which determines the performance of the photodiode. Clear? So SNR is equal to what? Signal to noise ratio. SNR is the signal to noise ratio is equal to the signal power from the photocurrent divided by noise. Noise are the number of noises occur in the photodiode, and the some noises occurs in the amplifier. So the noise power is equal to noise power from noise power from photodetector and noise power plus में noise power from what? From amplifier. Clear? So signal to noise ratio is the signal power from the photocurrent divided by the photodetector noise power plus में amplifier noise power. So now next one is the noise source in the receiver arise from the photodetector resulting from the statistical nature of the photo to electron conversion and the process, the thermal noise associated with the amplifier. Clear? So there are different number of sources. The sum of the noise occurs from this one, and that is equal and that are mainly due to the statistical nature of the photo to electron conversion process during the when optical energy is converted to the electrical energy. Maximum noise occurs due to the statistical nature of the photo to electron conversion process. And the next power is contributed by the amplifier, that is equal to the thermal noise associated with the amplifier circuit. Clear? So to achieve the highest or maximum signal to noise ratio, the photodetector should have what? Should have high quantum efficiency to generate maximum large signal power. Means the photodetector should have high quantum efficiency so that maximum IP current is produced in comparison to the input. Clear? And the photodetector and the photodetector and the amplifier noise should be kept as low as possible. If both factors is considered, means the IP output current should be very large, means signal power should be large, and the noise power should also minimum, then only the SNR can be maximized, because SNR is equal to signal power divided by noise power. When noise power is less, then SNR also increases, and the signal power is greater, then also SNR is increases. Clear? So sensitivity. Now next term is the important term of the photodetector, that is the sensitivity of the photodetector, which is describable in the terms of what? Minimum detectable optical power. Okay. Now minimum optical power which is required at the minimum optical power from the optical output from the end of the optical fiber cable is to be incident on the photodiode to produce what? To produce current. Minimum optical power is required for the photodiode to produce the optical to produce the output current, and that is the term known as the minimum detectable optical power, and that is equivalent to the sensitivity of the photodetector. So this is the optical power necessary to produce photocurrent of the same magnitude as the mean square value of the total noise current, or that is equal to the signal to noise ratio is equal to 1. Means SNR, when sensitivity is or minimum detectable power, SNR is equivalent to 1. Clear? So these are the different, this figure shows the different sources of noise or error sources in the optical fiber on the optical receiver. And first of all, this pic has been taken from the Gerd Kieser book, Optical Communication. Now see this optical signal from optical fiber cable. When it enters into the photodetector, this photodetection is of PIN, photodiode, and there are number of sources. The number of sources of noise in the PIN photodiode, that is one of the, it is the quantum noise, second one is the dark current noise, third one is the background, and the fourth one is the beat noise that is occur from the incoherent carrier, that is incoherent source. And when this photodiode is APD, then these noise occurs along with the noise occurs due to the avalanche gain, that is noise occurs due to the multiply factor, that is M, and that noise is excess due to the random gain mechanism. Clear? Now this photodiode, after the photodiode amplifier after that photodiode, if I say this is a photodiode and this photodiode is connected to the amplifier, but there is also some biasing resistor is applied when we are providing the biasing to the photodiode. Clear? So this one is the detector load bias, and this detector load bias provides what? Thermal noise. Clear? After this, amplifier is occur, and amplifier also provides what? Due to the input resistance of the amplifier, the thermal noise occurs, and there are number of active elements which is used in the amplifier. That active elements provide the what? Provide its noise, and there's surface leakage current is also occurs in the amplifier circuit, that also provides the noise. Clear? So this is the main block diagram is of the optical receiver, and these are the different number of sources which provides the noise. Clear? So equivalent circuit for the I have already told you, this is a biasing circuit, this is a photodiode, and this is the amplifier. So they all three are parallel to each other. So I can say the equivalent circuit of this receiver, this simplest receiver is, or simplified receiver is shown in this figure. This is a photodiode. This resistor and the capacitor is related to the photodiode, internal resistance and the internal capacitance. This RL is the bias resistor which is parallel to the photodiode, and this one is the amplifier which shows the input resistance, the input capacitance of the amplifier. Clear? And this one shows the equivalent circuit of what? Photodiode. Clear? Now let's say if I say the signal enters into the or strike the number of photons strike onto the photodiode, the output will be what? In the form of current. Clear? So let's say if a modulated signal of optical power PT falls on the detector, the primary current that is equal to IPH is generated, that is equal to IPH T equal to quantum efficiency multiply में Q into में P of T upon में H nu. This is the value of primary current, or I can say this is IP. Both are same, that is equal to quantum efficiency of photodiode multiply में electron charge upon में H into में nu multiply में input power which is incident on the photodiode. Clear? So now when I say this primary current, that is IP, we generally shows that this primary in the terms of power we always show that it is a mean square value of the current. So the primary current consists of DC value IP, which is the average photo current due to the signal power, and the signal component IPT. For PIN photodiode, mean square signal current, that is we are shown here, that is equal to I square, and this I square S is equal to what? I square PT. So I square S equal to sigma square S for the PIN photodiode equal to I square PT. This sigma is equal to what? Variance. Clear? Now if I say the photodetector is the avalanche photodiode, PIN avalanche photodiode, then this signal output signal current, that is shown I square S, is equal to what? Sigma square variance of the APD, and this is equal to what? I square PT. This is the output current in case of what? In case of PIN, that is a primary photo current, multiply में it's the multiply में what? Internal gain of the internal gain of the what? Internal gain of the APD. Clear? This is multiply में M square. So M is the average of the statistical varying avalanche gain. Clear? And as M is not constant, it is dependent on the temperature and it is variable, and that is the average of the statistical varying of the varying avalanche gain. Now if I say the input current is sinusoidal and is having a modulation index M, then I square PT, mean square value of the current, mean square value of the primary current, that is equal to sigma square equal to M square by 2 multiply में I square P. Clear? So the principal noise associated with the photodetectors are the, as we know, that is equal to quantum noise, dark current noise. The main basic noise sources in the PIN photodiode or the avalanche photodiode, that are the quantum noise, dark current noise, and this dark current noise is further classified into two types, or that is dark surface current. Clear? That is the surface leakage current. Clear? And the now first of all we will discuss about the short noise, and this short noise is also known as the quantum noise, which I have already discussed, pointed out in the few minutes ago. Clear? Now it arises, this short noise arises from what? Arises from the statistical nature of the production of and collection of the photoelectrons when optical signal incident on it. Means when I say the output from the optical fiber cable, the number of photons at the output of the optical fiber, when this strikes onto the APD or PIN. Clear? So there is a statistical nature of the photoelectrons when it incidents on what? Incident of the APD and this statistical nature, due to the different due to the varying statistical nature of the production and the collection of photoelectrons on the photodiode when optical signal is incident on, this fluctuation determines the what? Determines the lower limit of the receiver sensitivity. This fluctuation determines the receiver sensitivity, or you can say this also determines the receiver bandwidth. Clear? So this is one is the most important quantum noise, but because it determines the lower limit of the receiver sensitivity and also the receiver bandwidth. Clear? So noise due to the noise current, that is due to the short noise, okay, that is I square short is equal to 2 into me Q into me IP equal to M square into me FM. This is in the case of when photodiode is APD, but when photodiode is PIN, then is equal to 2 into me Q into me IP. Clear? And what is the FM? FM is the noise figure associated with the random nature of the avalanche process. This is the noise figure, and this FM is generally equivalent to the m की power में x, and x depends on the material of the semiconductor from which the APD is made. Clear? Now next type of noise is the photodiode dark current noise. Next type of the noise is the dark current noise. The photodiode dark current noise is the current that continues to flow through the bias even when no light is incident on the photodiode. Let's say if I say this is a optical fiber curve and the number of photons enters into it at the output of the optical fiber cable, and these photons incident on the photodiode. Now when I say if no photons strikes onto the APD or avalanche APD or the PIN photodiode, then also the output current is also flows through the bias. This is known as the dark current. Dark current means when there is no input at the photodiode, but still the current continues to flow at the output. That is the dark current noise. And this is combination of what? This is combination of what? Bulk and surface current. This dark current is generally shown in the form of what? Is shown in the dark current noise, that is equal to IDB, which is arises from the electrons and holes that are generated thermally in the PN junction of the photodiode. Clear? Means if you say that if you know the working principle of PIN photodiode or the APD, the electron suddenly gets heated out and it moves from to the output after the recombination. Clear? Now see now after hitting by the optical photons. Clear? Now when suddenly photons does not strike on the PIN photodiode or the APD, then those electrons also have some energy that they will move across the bias resistor. So this provides the current. So in the APD, these liberated carriers also get accelerated with the high electric field present in the PN junction, and therefore multiplied by the avalanche gain. Clear? So this dark current noise is mainly is more in the what? In case of APD, because in the APD electric field is there, and this electric field does not goes down even when the photocurrent does not photons does not appear on the hit on the APD. Clear? So this dark current is generally shown is equal to Q2 multiplied by Q into ID equal to M square FM into my B. This B is the receiver bandwidth. Clear? So when it is PIN photo, then it is 2 into my Q into my ID into my B. But this is case of APD and this is case of PIN. Clear? So the clear? So next one is the surface dark current is also referred to as the surface leakage current, which is the independent of the surface defect, that is equal to 2 into my Q into my IL into my B. Clear? So overall noise due in the photodetector, that is sum of what? Sum of short noise, dark current noise and the dark surface current. Clear? That is equal to, if I add these three equations, first equation, second equation and the third equation, if I add these equations, then you will get this one. Now next source of noise is due to the bias resistor. Clear? So amplifier input impedance is much greater than the load resistor, so that its thermal noise is much smaller than that of RL. This photodiode, this load resistor contributes what? Mean square thermal noise current, that is equal to 4 kBT upon my RL into my BE. So this one is due to the bias resistor or RL at the amplifier. Clear? This Kb is the Boltzmann constant and T is the absolute temperature. So next one is this is the important parameter for determining the performance of the photodetector. This is the SNR. This SNR is equal to signal power divided by the total noise power, and this, as I have discussed, that the total signal power is equal to what? Total noise power is equal to this one, which I have already discussed in this, and the signal power is the, for the PIN case, signal power, output power equal to what? I square is equal to what? I square root mean square value of IP, primary current. But when I say it is for the avalanche case, that is multiply what? M square, it is its gain. Clear? So the total power, so signal, just put the value of signal power here in this equation, and then photodetector noise power, that is equal to this one, put this equation here, plus the amplifier noise. This amplifier noise I have already discussed, that is equal to what? 4 kBT upon my RL into my B. This is amplifier noise or thermal noise current, that is, if we add this on putting this value, we will get, this is the SNR. Clear? So when PIN photodiode dominating noise current, when PIN photodiode is used, dominating noise current is mainly due to the quantum noise and the active element of the amplifying circuit, and also due to the thermal noise, that is due to the RL. Clear? For the avalanche photodiode, this thermal noise is of less importance as compared to the photodetector noise, because in the avalanche photodiode, the dark current suddenly increases, dark current noise suddenly increases, and the short noise also suddenly increases. It can be seen that the signal power is multiplied by M square in case of what? In case of APD, and the noise, short noise, is also get amplified by the M square into my FM. Clear? Now this surface leakage current is not affected by the avalanche gain mechanism. The noise figure increases with gain and there always exists. So there should be some optimized value of M, so that signal to noise ratio get optimized or get maximized. Clear? So this one is the SNR. So there should be some optimized value of M, so that the SNR get increased, because M is also in the numerator and also M also in the denominator. Clear? So this one, M is also in the denominator and M also is on the numerator. So M should be optimized so that the SNR should be maximized. So for getting a maximum, of some equation, we will just do what? We will just do what? Differentiating of the denominator and put the value of M equal to, when put the value of this equal to 0, and we'll get the optimized value of M. So optimum gain at the maximum signal resolution can be found by what? Differentiating the equation, differentiating this equation with respect to M, and the this SNR is setting to 0 and we will solve the value for the M. Clear? So the optimized value, for the M is equal to what? 2 into my Q into my IL plus 4 KBT divided by RL upon my X into my Q IP by IP plus my ID. And this X, value of X depends on the what? Depends on the material of the semiconductor from which the APD is made, and the modulation index is, we have put it, that is equal to 1. Clear? So optimized value of this one is equal to this one. The book I have referred for preparing all the slides and the content is from the Optical Fiber Communication by Gert Kieser, and the next book I have referred, it is the Optical Fiber Communication of Principle and Practice by the John M. Senior. Thank you.